Yes. So who am I? So I'm Sam Williams. Hello. I work just around the corner at a company called BJSS. We're, I'll get this right, a technology and business consultancy. You can probably guess from my title, I'm sort of more on the technology bit of that. So the good fun bit about that is I sort of get to stick my nose into loads of different projects, which is sort of what I like doing because I can learn lots of stuff, but run away before I get burnt. It's not the official pitch for my role. But yeah, I mean, this was sort of a finance-related talk, and I get asked to do finance-related talks because I spent ages working in banks. So I have sort of a good decade working in big old banks. I did some quite cool-sounding stuff. So I worked on trading systems. I was building social networks when everyone thought it was a good idea to build your own internal social network. It didn't work out so well. I spent a bit of time building like a digital delivery department for a bank. So I saw more building projects inside banks. I've seen a whole lot of stuff built inside banks, basically. And then during the end of my time in finance, I had a role that was supposed to be looking at sort of threats and opportunities in the fintech space. So I met with loads of fintechs and sort of had a chat about what they were doing. And they would largely tell me how whatever they were doing was going to annihilate banking or something to that effect, or make us all rich. I wasn't quite sure. But what I'm going to talk about tonight is consensus algorithms. It's like confession, actually. I just wanted to talk about consensus algorithms. I never got the chance to use them in finance. I'm going to come up with a totally false finance example for consensus algorithms. But I didn't actually do it, which is a shame. Do you know when you're working and you're building stuff in your day job, and you go home with like this nagging feeling that this could be so much better, and so you go and read around the subject and you kind of learn loads of new things, and then your project finishes and you're on to the next thing and it's not really useful. And that's happened a few times in my career, and several times I found that the thing I wish I knew or had known or had been able to convince people that we should do was consensus. And so I became quite obsessed with it in a healthy way, I'm sure. So I really enjoy consensus algorithms. I think they're amazing. I really enjoy distributed systems. I think they should be so much better than they are. And I think part of the reason they're not is we don't use enough consensus. So I've said that word a lot. I mean, what does it even mean? So what is consensus? Well, I've done a good bit of Wikipediaing. So consensus decision-making is group decision-making, where a group of members develop to an idea and they agree on it for some sort of common goal. So it's a group that they agree and have a common goal. Okay, I get that bit, but like computers and stuff. So consensus in computing is like a fundamental property of distributed systems. Consensus enables faulty, rubbish computers, which is what we have, to build reliable systems. Key thing is systems. It's sort of easy to build things with lots of computers if you don't actually need to build a system. System is where lots of things work together to form one cohesive whole. So if you need a system, which is many things working together in a cohesive system that sort of works and is non-faulty, you will need consensus. So basically it's about agreeing. Specifically it's about computers agreeing. This was a really interesting week to Google consensus, because just the amount of articles that came up that were not what I was looking for. So it's about agreeing. It's about agreeing in conditions that are kind of tough, and it just happens that they are actually the situation that most computers operate in. Computers sort of just arbitrarily pause, which is nice. They just lose messages. They decide that they've got too many messages in their buffer, so they're just like, nah. Someone else turns them off. Cables get unplugged. This really happens. Sometimes you think to yourself, maybe it's got better this year, and maybe we don't need all of this stuff. But then you actually try and build a system in the cloud or just anywhere really, and it's all just terrible. So it's about agreeing. It's about making reliable systems. I'm sure also that it's not terrible. The cloud's great. So why would you do this? We know we want reliable systems, but surely we all build reliable systems. Well, one reason might be you want to build like a genuine differentiator into your product. So here's a bunch of products that, while they have lots of features and will plug themselves as being awesome for many different ways, their primary feature is their capacity to agree. So you've got like CockroachDB, this new Cosmos DB from Azure, Fauna, all of these are systems where you can have loads and loads of nodes. Many of them can tolerate global distribution of nodes, and they can all provide you a consistent view of the data stored in that database. They can all agree what the data in the database is at any one time. And that's quite incredible. It was not that long ago that you really couldn't get these products. Foundation DB, in about 2011, I was really excited by Foundation DB. It did all of the things that I wanted a distributed database to do. It was fault tolerant, it was linearly scalable, it was consistent. So I was playing around with Foundation DB. They even sent me a T-shirt. It was one of those VC things. They send you a T-shirt if you sign up. So I've got a T-shirt. And then in about 2012, Apple bought Foundation DB, and it vanished. They paid some manner of hundreds of millions, I think, of pounds to make it vanish. And I presume they used it internally, but that was a real shame. But basically, if you were around in 2011 and you understood consensus, you could be really wealthy. Obviously, I didn't, and I'm not. So anyway, Apple tossed that back out into the open source about a year ago, so you can still play with Foundation DB now. It's kind of lost a bit of its momentum. And there's these other products that have also evolved, and they're also really cool. Goshawk DB, my buddy wrote that, so you should totally check it out. But yeah, I mean, it's not also like these shiny, amazing products that can do things that you didn't expect that use consensus. We actually probably all use consensus in our systems without really noticing it. If you use any kind of orchestration system, the likelihood is it needs a consensus algorithm in order to do what it's doing. If you need to spin up loads of machines and you need to register the right names against those machines, that's essentially an agreement problem. So most orchestration systems, most service discovery systems, most of your sort of configuration systems which you deploy with your microservices, under the hood they have some kind of consensus algorithm. So even when we don't know we're using it, often we are using it. And obviously there's blockchains. So blockchains, they do use consensus. Fundamentally, blockchains are about agreeing the value of a ledger. Now the specific type of consensus that blockchains use is this thing called Byzantine consensus, which is like agreeing to a value when maybe there are some people that don't want to. So it's a little bit trickier than normal consensus. It's also a little bit less useful generally, but don't worry about that. So consensus, really important in loads of systems. If you want to build a distributed system, chances are you're going to need to understand consensus. Even if you choose not to use it in your system, even if you choose to build a system where nodes don't agree, you're probably going to want to understand why you did that. So the thing is, apparently we're building distributed systems all the time now. Like every project I end up looking at, someone will tell me that this is a distributed system. Basically because we use loads of computers. We literally throw computers at everything now. You can't build a website without 10 computers. So why don't they look more like the databases we were just looking at? When I think back to my career in finance, I saw this, well not this picture, because this is not the picture, this is NAS, but whatever. I saw a lot of pictures like this that described the internal landscape of the bank, or indeed many bloody enterprises. You've got services everywhere. They're big, small, whatever. They've got lines between them. Often there are great big queues between them, all sorts of industrial looking things between them to make them do their job. That's a lot of things that I find it difficult to believe are forming a system. It's more like a network of things that have opinions. More like our parliament. So let's go into this problem a bit deeper. What are services like? How do they operate? How do they think? So here's a contrived example that never happened. And much like the last one, involves a transfer. It's a little bit silly, but some bits of it are real. So you work in a bank. Everyone assumes that you have some big, clever system that holds your accounts. And it's all ACID and transactional and so on. What really happens is you have multiple of them, and they're not very clever. Because banks tend to buy other banks at an alarming rate, and then sell off other bits of the banks. So you have lots of different systems that all hold bits of people's accounts. So here we've got some old system that's got Bob's account in. We've got a slightly less old system that has Alice's account in. And we've got a shiny new compliance system which has somehow unified them both. So if we imagine a scenario here where we want to transfer some money from Bob to Alice, but we only want to do it if compliance says that it's legit for both of them to be doing stuff with money. So how might we do this? Well, let's give it a whirl. First off, let's check with compliance. Is this screen matching this screen? Yes, cool. So let's first check with compliance whether we can do this. First step, all good, that's fine. Second step, let's take 10 of these unitless currency things out of Bob's account. Cool, that'll work fine. And then let's pop them in Alice's. And I suspect you know some of the things that could likely go wrong with this scenario. And they can go wrong so easily, it's just mind-boggling. So we'll check with compliance again this time. We'll go and speak to old system, but for some reason old system does not reply. Let's just try it again. It'll be fine. So we do it again, as we almost always do, because it's REST. What else do? You just, come on, try it again. At the end of the day, Bob now has 90, not the prescribed 100 that one would imagine he had at the beginning. And from this godlike position, looking down on the state of the systems, it's very obvious. But it's actually really tricky to debug this and figure out what happened and why it's all broken and why you want a new job. So this kind of stuff goes wrong all the time. You can lose money, you can magic money out of nowhere, you can totally break the laws, you can start things happening and then you have no idea whether they finished or not. And that is in the scenario where you have one system, one person, one process using the system. When you introduce concurrency into that, and it's just all bets are off. You've got no idea what's happening. So how do we solve this? Because this is obviously not what's happening. And what we do is we throw engineering at this, right? So classic solution in the bank is you get some kind of enterprise service bus thing. You can kind of imagine it being screwed into the floor. It's so enterprise. And you can put events into it and they'll be totally durable and safe and everything's fine. And that might work. You can, as we've just discussed, we can go for an event-driven architecture. And this is a much more grown-up approach. This will actually get you a lot closer to your end result. But if you've got two rubbish old systems in your bank, chances are you do not have the money to invent a shiny new third one that replaces them and creates a whole new domain of data that models these two weird systems that no one really understands anymore because you bought them and everyone's left. So you might create a new aggregate service that sort of deals with these little situations where you want to do things across systems. You might give up, stick it all in one great big transactional database. You could do that. Someone will probably come along and tell you need to turn your database inside out and make like the universal log the truth. Has anyone come across this? This is kind of like Kafka thinking. It's actually really awesome. And the guy who wrote Kafka is a genius and writes some really good books. You could read them. But at some point you have to question whether you just wanted to move some funds in these two services. Do I really have to invert my entire universe to run off a log? Or you'll do what most systems do, which is pretend you're doing eventual consistency. But you really don't have any model of consistency at all. It's just inconsistent and no one's really noticed yet and possibly hasn't happened yet. So this begs the question, or has for many occasions for me in my career, why don't we use consensus? Like, when I look down at, can we go back in slides? Who knows? When you look down at this system from like your God view here, and you can see all of the data, you can see that you just need these systems to just agree, right? You've got some money, you've got some money, you can all do it. So just agree to make this happen or not make it happen together. Stop asking me to boss you around with all my little crud actions. So why don't we use consensus? So I think one thing that puts people off is that it's impossible, which is a real shame. So 1983, these clever people, they set about to determine, because it was turning out that building systems was really hard, and so they wondered why. And so they did some maths and they discovered that it is in fact impossible. If you have just one faulty process in a distributed system, you cannot achieve consensus. So that isn't the end of the talk. So a little while later, another clever chap called Leslie Lamport had decided that while this is probably true, maths can be quite specific. And in the real world we can just be a little bit more loose and gung-ho. And let's say we want to achieve consensus, but we're not quite so bothered about the fact that it's impossible in the specifics. We just want to make it real for most of the time. And you can do this with things like timeouts. So one of the fundamentals of the impossibility proof is you would need to know that a computer is responding or is dead. So is that computer alive or faulty? And do you know, if you just assume it's faulty, but your algorithm can tolerate that, that's fine. So one of the things that you'll get in consensus algorithms is you may occasionally assume that a system is down and broken when it's actually not. If you're okay with that, then you can have consensus. And it turns out most of the time that's fine. So, early 90s, everyone was convinced that it was just like doom for computers, just make bigger ones and not bother. Leslie Lamport wrote what has to be the most eccentric and odd computer science paper ever published. Rather than the usual sort of standard approach of describing a problem in computing, outlining a solution with some sort of pseudocode and then showing some results, what he did was, he described a mythical people that lived on the island of Paxos. And these mythical people who lived on the island of Paxos, they were jolly nice people. They generally got along and agreed on stuff, but they needed a way to lay down laws. So they needed a parliament, and this parliament would be staffed by Paxons, these lovely people that lived on the island. But they were tradesmen, and they were very rarely on the island. So they would only really be able to function. The parliament would only function every now and then, really, when people were about. And it might not be the same people in the parliament who were there last week, and they would have to send messages by like pigeon or thrown on rocks or whatever. So basically, it was an incredibly unreliable parliament in many respects, and it just so happens that it has exactly the same unreliability problems as distributed systems. So brilliant. So we have this thing called Paxos. It's an absurdly interesting paper, and he does outline a sort of algorithm in it that solves consensus. And actually, Paxos is like the most fundamental, arguably the most fundamental algorithm in distributed computing. The only one that I would say is arguably more important to it is the other one that Leslie did about Lamport clocks. So he does, in fact, solve consensus. The Paxos algorithm solves consensus for us. So we're done, right? We just use Paxos, and we can solve all these problems. So obviously, that's what everyone's doing. It didn't quite pan out that way. So Paxos is incredibly useful, and is used all over the place. And one of the places it was used first, in real anger, was inside Google. Google needed a consistent system to span all of their giant data warehousey whatnots of all their people all over the world. And so they built this thing called Chubby, which is a lock system, so that all of their other products could be built to use Chubby to get and release locks. And they did it using Paxos. And then they wrote a paper complaining about it. While the core Paxos algorithm is well described, implementing a fault-tolerant log based on it is a non-trivial endeavor. Paxos made life an engineering perspective. And if you read this paper, it basically reads like a sprint retrospective where everyone's just pissed off. And people listen to Google, and so Google said this was really hard, and so no one does it. And that's kind of what happened. And then a little bit later, there's this whole other paper that was published. Has anyone heard of Raft? Those people have always heard of Raft. So Raft is a consensus algorithm. And literally the title is In Search of an Understandable Consensus Algorithm. And he goes on talking about how Paxos is just, one can't understand it. And this is a real shame, right? Because I'm not sure it is ununderstandable, if ununderstandable is a word. Then obviously people will complain that it's slow. Paxos is slow, consensus is slow, which I always find odd, because if you need to agree something, if you need a system that is consistent, then you need consensus. If you don't need to agree, well, obviously it'll be faster, but whatever. So why is Paxos hard? So believe it or not, I do understand Paxos, and I actually think it's not that hard. But it did take me a while to get there. And I think partly that is because the paper is just crazy. And also it has some fundamental little hiccups in it for the way that we normally learn stuff. So problem number one is understanding what egalitarian means, which is not something you normally have to do to understand an algorithm. It's posed in terms of a parliament, and our parliament is not egalitarian. So any Paxon that comes into their parliament, their sole purpose is to agree with everyone else. That is not what happens in parliaments that we know. So that can really throw you. So we'll see that in a moment when I try and show you this. The second one is quorum-based thinking. When we think about a distributed system, we often think in our head, as long as I can talk to any node and it gives me the right answer, then it's working. But the objective of consensus isn't to make every node have a copy of the truth. That's replication. It's so that the system as a whole understands what the truth is. And so the system is represented by a quorum, or majority of the nodes. So any one node might not know, but a quorum does. And obviously it's not an algorithm, it's a story about Paxos. So, I mean, that makes it hard. But I mean, all that aside, I'm going to have a little go at explaining Paxos, because I think it's fun and genuinely one of the most important algorithms that you can learn or not learn. So let's have a quick go. Let's try and do something that's remarkably difficult, apparently. And what we're going to do is we're going to build a really trivial database. And I say trivial because it can only store one value once. So it's somewhat limited. What could you store in a database that you can only store one value in once? Well, I'm thinking like the meaning of the universe. That's not going to change. It's going to be fine. OK, so we're going to go along to one of these nodes, and we're going to say the answer is 42. Please persist that eternally. So let's think about what state the database would be in at the moment. So for Paxos to work, it's a two-phase algorithm, although it doesn't have to be, but let's not worry about that. And the first phase is the promise, and the second phase is the commit. So we're going to have two little bits of information that's stored in each node here, a promise and the value. No one's made any promises at the moment, and there's no values in the database, so we're good to go. So we'll go for the first phase of Paxos. Let's ask all of the other nodes in this system to promise to do whatever we say. That's pretty much what the promise phase says. You talk to all the other nodes, or at least a majority, and you say, well, whatever you think, I'm the boss, what I tell you goes. And the nodes reply with a sort of promise. They say, OK, for the number you gave us, 10, we promise to do whatever you say. But if someone comes along with a bigger number, we might just ignore you. So we end up in this state where they've all promised to do whatever 10 says. So that's fine. This is the happy path. So having replied to that first node that they all promise to do what they're told, the first node will then just say, OK, we'll commit the value 42 with the promise that I asked earlier, which is this 10 number, and great, it all goes fine. So there you go, guys. That's Paxos. Job done. And to some extent, it is, which is odd, isn't it? Why does everyone think it's so hard? Now, I suppose I haven't really been quite honest yet. So let's go a bit further into this. What happens when computers fail? Which they do. Let's try again. We're going to set this answer to 42. We do the same thing. We ask them all to promise, do as I ask, you lot. But only one of them gets back this time. But that's actually OK. So we've got two nodes that have made the promise that they will honour 10, whatever you say, right? And 2 is a majority within 3. So this is quorum-based thinking, so we're happy with that. So we just carry on. Let's commit the value. Job done. We're still consistent. This is still a working database. Still can't give the wrong answer. Paxos under failures. All good. So computers rarely fail. They just sort of go away for a while, and they come back. So what do we do about that? Well, to demonstrate that, I need a couple more computers. So what I'm going to show here is a 5-node system. And we're going to try and fudge it. We're going to try and set a false value for the answer. So if we look at this, the two outlier nodes at the top, they've both made a promise to this number 2 at some point, but they've not got a value. So they made a promise, and then no one ever came back and told them what to do. But the middle nodes, they've actually made a promise to 10 and committed the value 42. So the system itself has decided the value is set. It is 42. It must never change, or that would be a violation of consensus. But let's try and fudge it. Let's say we say to this node that hasn't seen the value, so maybe we can get away with it, that the answer is -1. Well, he'll have to contact a majority in order to get this done. So he'll pick 2 nodes and say, he'll pick a random number, a nice high number, so he gets it through. Promise me, I'm 88, to do as I say. And they'll both reply. But because this is an egalitarian parliament, the node that has seen the number 42 will try and let this guy know. It'll be like, you want to be careful here, because I've actually already committed 42. So rather than trying to force -1 into the system, what the node will do is honour the properties of the system. And it will then recommit 42 back into the system. And so what you get is a bunch of computers that work together to ensure consistency, even when clients are trying to force inconsistency into it. So if a majority has ever made a decision, no minority can ever overturn it. And the basic principle there is, if you take any 2 majorities inside a system, they will always overlap. you will never be able to take a majority and get them to make a decision that a later majority will not have to try and overturn in order to get a value committed. And that's the fundamental of that quorum-based thinking that I was getting at. So is that it? Have we solved Paxos? Sort of. It's actually a little bit harder than that. So what we have demonstrated is setting one value once, which, as we've demonstrated, has its uses, but perhaps they're a little limited. What you really want, what gives you like the magical powers of Paxos, is to be able to build a finite state machine that is distributed over a whole load of machines. Once you've got a finite state machine, you can take any algorithm that you can run locally, and you can run it on a distributed set of machines perfectly safely and fault tolerantly and fast and all that goodies. To do that, you need multi-Paxos, which is like running Paxos, 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 which is hard to say. But it's not actually more complicated than what you just learned. It's just repeating it. Reconfigurations are a little bit tricky. So, you know, if you've got a 5-node system and you want to pump it up to like a 9-node system or a 16-node system, it's not the easiest thing in the world to do, because you need to, at one point, switch from having a majority that's 3 to whatever it is in the future, and make sure that no decisions ever get through where they shouldn't. And then there are all of the optimizations. What I showed you was a 2-phase Paxos, which is kind of why people complain about being slow. But you don't really need a 2-phase Paxos. There are plenty of ways to optimize this. You can do it in sort of 1.5 or 1 in the fast case. And then there's the whole timeouts thing. Like, when can I say that I've not got a reply? What's the right barometer for that thing is dead? So it does get a little tricky in the implementation, to which Google will attest. But why would you learn all of this, aside from all of the magical stuff that you could do and go and make yourself rich by building a database? Well, I fundamentally think that it can simplify systems. And I think that because systems that agree present themselves as one system. So if you have a global database that can agree with itself, you just have one database. You don't have to worry about all of these tricky little nuances that come from inconsistencies and eventual consistency and having to have some mighty great queue that is the lord of your architecture. So I really like it, and I don't think we use it nearly enough. Things didn't stand still after the Paxos paper. There have been loads of papers improving on Paxos and releasing new consensus algorithms, things like Raft, since then. There was even one this year by an amazing person called, amazing lady, Heidi Howard, who works at Cambridge. You should definitely read her stuff and watch her talks. They're awesome. But yeah, don't believe the FUD. Consensus is entirely possible. It's not even that hard in some circumstances, you know, and actually, I think a lot of the things that we do, the complete re-engineering of our solutions, are to some extent harder. We throw in so many products and technologies into our architectures these days, and sometimes I wonder whether just learning an algorithm would be simpler. Paxos is just one consensus algorithm. There are others. There are simpler ones. There are faster ones. There are more complicated ones. They're all pretty cool. And also, if you learn Paxos, you have like a developer superpower, because no one else knows it. So, you know, that's fun. Okay, thanks a lot. That's my lot.
Can you repeat the questions, please?
Oh yeah, sure. Confused me. I didn't think there had been any. Yeah, any questions? Hello.
Can Paxos deal with a malicious component within?
No. It's fundamentally about honest nodes. The Paxonian people were lovely, so they didn't try and cheat or lie. Yes. So there is. That's when you get into the tricky business of nodes that may be dishonest, messages that may be corrupted. Did I repeat the question? I totally didn't, did I?
That's fine.
Okay. Hello. Go for it.
Do you know any production usage of it?
Of Paxos, production uses of Paxos are everywhere, although you often don't know it. So any of the large, like basically if you're building a large distributed system, you have a choice. Are you going to build a system that is consistent, or are you going to build one that isn't? And you can get away with building a lot of systems that aren't consistent, because they don't need to be. But a lot do need to be. And so you often don't really realize that Paxos or consensus is there, but it's underneath the covers in so many systems we use, whether it's things like the cloud providers we use that build large distributed systems that we use without really thinking about it, that are all built on consensus algorithms, whether it's all of the things I showed you, like the orchestration systems or the things like Zookeeper and so on, all of the little things that we use to pin our microservices architectures together but don't really appreciate that they're doing really clever things under the hood. Yeah, I mean, it's literally everywhere. Yeah. Cool.
But if I'm building a public network,
Mm-hmm.
there will be certainly malicious people.
So if you're building a public network, there will be malicious people. So yes, if you do not own the nodes, consensus algorithms are probably not for you. Although I think that's debatable. So one of the great claims of blockchains is that you can have all of these nodes for organizations that don't trust each other, and the computers will all just work because of Byzantine consensus. And I'm not entirely convinced that that is the right approach. Lots of things in the world operate on some degree of trust. And we have things to fall back on, like the law, when people break it. When you interface with things like a stock exchange, it doesn't make you operate under some sort of strange game theory plan like blockchains do in order to work. It just says if you break the law, you will be prosecuted. And I've always thought that's a little odd about blockchain solutions. They seem to have ignored the fact that we exist in a system that has ways of encouraging good and bad behavior. So yes, you will have dishonest actors, and maybe that's a reason not to use a consensus algorithm, but I wouldn't bet on it. Hello?
I'm actually building a database.
Ah, awesome.
Project
Okay.
in university
Uh-huh.
using Raft instead of Paxos.
Yep.
Easier to use.
Yes, yes.
One of the problems I'm facing is how would you verify your implementation is correct? Foundation DB does it by simulation using mocking all the disks, all the networks, and try to inject faults. How do you think is there a better way?
Okay, so really good question. So it was so he's building a database, which is awesome, using Raft, which is good. Lots of people use Raft because actually it is on the whole simpler. It's one of the things that paper achieved was to describe an algorithm really clearly, so people could actually build it. So the question was how essentially to test a distributed database, right? Yeah. And that is what makes distributed systems much harder than non-distributed systems, is all of the things that can go wrong will. It's very hard to run it on your own system. So I don't think there's any one right answer to how to test a system. Foundation DB went like way off the scale in what they did with simulation, and they basically built a simulation layer for the database that tested all of the scenarios that they wanted the database to achieve before they actually built the database. So if you've got the time to do that, then good on you. I suspect, like most things, it's just a balance. I think a bit of formal methods helps when it comes to building databases, a little bit of TLA plus to model what your database should do, because they're such complicated things that it's useful to know that you're actually going to achieve what you set out to do before you try and do it. But yeah, no good answer to testing, I'm afraid. Probably should have a good answer to testing. Hello?
So your one of your first examples was about the different bank accounts.
Yep.
And then you went on to describe the Paxos algorithm as
Yeah.
kind of single value.
Yeah.
Finding it hard to make that leap into like how
Yeah.
algorithms to solve that original problem.
Okay, so that was I described how to basically set one single value with Paxos, which is a long way off getting a whole bunch of systems to agree that something should take place.
Because they're doing different things.
They've each got a different role. So what you're looking at there is you're using consensus to agree not on what they're doing, but whether or not they're all prepared to do it. So the paper you want to look at there is consensus on transaction commit, where you use exactly the process I've just showed there, not to set a value and keep that consistent, but to all agree whether the value is success or failure of a transaction committing. And so you're still agreeing on one value, really. But what your metrics for deciding whether that is true is in fact the case, are domain specific then. Hello? You don't give up dynamic. So do you give up dynamic scaling in this situation where you have to know the total number in order to form a majority? You don't, but you do have to. You can't just ad hoc add nodes. Right? So you have to use the system. What you typically do is you build in what the shape of the system is as one of the values that the system all agrees on, and then you use the same operations to update that value. So you add a whole bunch of nodes that aren't doing anything, and then you say to the system, this is no longer a 5-node system. You use Paxos to agree that this is actually now a 10-node system. And after that point, they all start interacting. But yeah, you can't just add them. You have to think about how you add them. Hello?
So as I understand it, banks kind of are using consensus algorithms for like distributed ledgers, or they're looking into it, or I don't work in banking, so I don't know how far along that is. Is that what you mean when you say they should be using it, or your idea is something that they should keep in?
So, should banks be using things like this? Are banks using things like this? So my experience of finance IT is mostly internal. So a lot of what gets talked about with things like distributed ledgers is interbank processing and parties that don't necessarily trust each other communicating on one ledger, which is not really what I have any experience of. And yet lots of banks are looking into doing that. I have run some proof of concept projects inside a bank to use things like blockchains to model these kind of systems, but not for doing transactions, just as a good technology to build on top of. How do they do transactions between systems at the moment? Well, with just about every approach imaginable. So if you remember that slide where there were loads of boxes and it just looked like a crazy mess. Big organizations have tried everything, and they normally still are. And now they have systems from the 80s that are still running. So they've done everything somewhere. So the answer is always sort of yes, they've done that. It's more interesting, I think, to get a useful look at what works now, is to look at some of the challenger banks, to look at how places like Monzo do it, which do much more like what we were talking about here. They do event-driven architectures, they build on top of things like Kafka, because those are proven ways of doing it that, that aren't just some lunatic who's into consensus rattling on. Cool. All good? Thanks a lot.